So we've heard from Jason, Peter and Richard, and it's the theory that we were trying to convey. It's in the lab, and there's two questions that you're probably wondering, and it's a rhetorical question maybe from me. How does that theory relate to practice, and where are plants in this story? And it's probably a bit of a bent for the Riverina branch that we see ourselves as soil scientists but also agronomists all rolled into one, because most of everything we do has to relate to growing of crops and pastures and things like that. Now, where the connection comes through from a soil physical point of view is through what was originally described, I think, by, well, what I've found, Feen and Beale, and then described in the diagram on the right of your screen there by Lady in 1985. And the soil physically, it provides water, it provides aeration, and it provides a structure for roots to hold plants up in. And if water is too hard to suck out of the soil, the plant growth will be affected. If there's no air in the soil for root respiration, the plant will be affected. And if the soil is too hard for roots to penetrate, as Peter pointed out in his talk, well then the plant growth will be affected. And so Leahy described these three things. He defined them with literature research and also research of his own. So a moisture content at a drained upper limit, field capacity of minus 10 kilopascals, a moisture content at plant wilting point of minus 1500 kilopascals, aeration porosity between 5 and 10%, depending on who you read, a penetration resistance of 2 to 2.5 megapascals. So you can see on the right here that water content sets the limit for that soil in A. In B, we've got our mechanical resistance limit at this moisture content here and our aeration limit here on the right. So those boundaries come together, and we've got a smaller non-limiting water range here because it's pushed it in. Strength and aeration have decreased your happy range for the plant. And then again, we've got this soil here, which is really tough, and it's probably poorly structured, and so we've got an even more reduced non-limiting water range, or least limiting water range. Now, I picked this one out. Richard did send me a graph. I chose not to use his because he's in the audience and he'd critique what I say. And the other reason is that this is still being done, 2020. It's a recent paper. It's the references there. It's exactly the method that Richard was talking about. It's taking intact cores. These guys took 96 cores, 5 centimetres diameter by 3 centimetres high in the surface soil. They put them all on tension tables, and they did a penetration resistance in the lab, all on undisturbed cores. And the results, I think this is a pasture, this is a cultivated, and we've got some conservation tillage techniques in here. And your field capacity here, your plant wilting point here, this is penetration resistance, and you've got your aeration porosity. And between the two, in this grey area, depending on where your bulk density is, the difference between that line and that line sets what your non-limiting water range is. Now, a couple of these curves are based on theory, and these are measured. That's fine in theory, but I'd like to take this into the practical world and get away from what we do in the lab, because my history is I started in Deniliquin at the end of 1989, and everything we did regards physics and irrigation related to what you've just heard. And then you get out in the paddock and you see these sorts of things, and I'm standing there with my corer and I'm going, well, where do I sample? And if I sample here, what relevance has that bit of soil got to the way water's going to flow here? Because I've stood in these paddocks and stood there for 15 minutes or more while water just runs down those cracks. So conventional soil physics for rigid matrix soils out of North America or Europe, they generally don't, well, they certainly don't apply to where I live out on the riverine plains, where soils are dominated by clays, 30 to 60%. And so my history of my work at Deniliquin has been to move away from laboratory measurements to using in-field sensors, and as technology has grown, the ability to do that to get temporal resolution and better understanding has just far exceeded what we could do with point-in-time hand sampling. So there's an example here, and so I'm going to look at that aeration limit first, then I'm going to look at the structural, and then I'm going to bring it to the plant. So we're looking here, this is wheat variety trial on a chromosol and on a vertisol, and we grew the wheat as a normal trial. We had it bunded, and when it got to flowering we put water on, so there was surface water above the soil, and we kept it on there for 2 weeks. It was on for 16 days and here on the vertisol and 14 days here. And you can see we've ponded water here, and there's really no significant difference between the control, which is the solid, and the waterlogged treatments is, what's that, Korak and Cobra, I think. The yields were a bit lower in those two varieties. But really, you know, you look here, they're all around the 7 to 8 tonnes. They're really good crops, even though we kept water on it flowering for 2 weeks. But here we go, we're on the vertisol, and we've got season length. So these are short season, these are long season. They've all been planted at the same time. But the short season lines seem to be even affected, irrespective in the control, and there's a significant difference, particularly here in the longer season lines, between the control and the waterlog. We say, well, waterlogging's had an effect. But why didn't it have an effect here? We see bottom, we've got the shaded area, which is the period of waterlogging. They coincide. We started a bit later on the chromosol and we finished a bit later on the chromosol as well. Rainfall, this was in 2016. It was a really wet year. So these crops, this is matrix potential up the top in the surface soil. We're coming out of winter into spring, and that's drained amylipid at minus 10 kPa, and these soils are both saturated. They've gone that way through most of the winter. They've grown happily, even though it's saturated, because it's been cool. And then we come into spring, it starts to dry down, and we give them a hit, and we put the water on, and we've ponded for this period. All these dates line up. It's been saturated through there. The solid is the control, and the dashed lines, see, they stay waterlogged, and then they start to dry down here. And the solid is the control. You can see it's drying here, then we get another big rainfall event, and they go back to waterlogged. So they've had this period of waterlogging. If you only had matrix potential, or you're only looking at water ponding, you'd say there was no difference between those treatments. It's saturated. But the difference here, and what explains the response, is that I'm also measuring redox potential. And redox potential at EH of less than 350 millivolts indicates that there's no molecular oxygen left in that soil. And so that's this aerobic threshold through here at 330 to 350, somewhere like that, but we've got to draw a line somewhere. And you can see in the chromosol, well, we put the water on and aeration, like oxygen, redox, drops here, and we've got quite a small period here where the treatment, I think that's about a week, actually is anoxic. So it's waterlogged, but it's also anoxic for this short period. And then obviously this vertisol, it's double the length of time, even a bit more. And then we come out here with this rainfall event. The chromosol drops down a little bit. It's not really affected by that rainfall event. But the vertisol, which had been previously waterlogged, it goes down through another anoxic period. So you can measure aeration porosity, you can measure saturation, but it doesn't necessarily actually have any bearing on what the plant's experiencing. If you want to know what the plant's experiencing, you have to actually measure the variable that's affecting plant growth. Yep. Penetration resistance. So we've got matrix potential here, and I credit Cliff with this. So this is a strength potential relationship. I can't remember how many soils we did this on, so I had matrix potential set up, and then I would go around on a drive around once a week or something like that. I would walk around trying not to disturb the crop, and I would take penetration resistance readings and I would match them up with a matrix potential. This is at 30 centimetres. These are vertisols. You can see as they dry down, matrix potential, that's actually should be negative, but that's drying. and 60 kPa is a crop threshold that I consider to be a trigger point for irrigation, and it's quite happy. So that plant there, strength is not, these soils here, strength is not going to be a limiting factor at 30 centimetres in those soils. The vertisols and chromosols here, they're all really kaolinite, you like, clays. The difference being the topsoil, but they all group together, R squared of 0.9, and you can see here at around 30 kPa, which is about half when I would normally irrigate these soils, they're getting too strong. So you look at that, hard soils, they're a real problem in the riverina. People have been talking about bulk density. I regularly measure bulk density, certainly 1.6, 1.7, even 1.8, and there's good crops growing in these soils. It's just the nature of the beast out there. What were the yields? The 3 vertisols, the other group, I can't remember why I split them out. I think they're self-mulching and these are sort of non-self-mulching. The duplex, chromosols and sotosols, and what I thought were 3 problem soils. Really, is there any difference? You know, you could sort of maybe draw some lines there. But it's not soil strength that's driving yield. In 2014 and 2015, when I was looking at these crops, and the other bit in there is that yield. So remember yield. The key driver of grains per metre squared in 2014 and 2015, which was a normal sort of rainfall year, was either poor layouts and a little bit of waterlogging in spring from poor drainage, or irrigation's not happening on time and there being a stress period. So the number of stress days, it's either wetter than minus 10 kPa or drier than minus 60. And they'll accumulate those days, plot them against grains per metre squared, and we've got 70% of the variation in grains per metre squared accounted for in either too wet or too dry. 2016 was a really wet year. It was wet through winter. It had no impact on grains per metre squared, but what it did affect, because of the timing and the stage of crop growth, it affected tillers. Roughly 50% of variation in the number of tillers was related to the number of days that soil was saturated. When you plot these things against yield, they're pretty much a straight line, because there's compensation in the number of grains in the head and in grain size, and here again there's compensation by the plant in grain size. So there's a timing effect, and yield is also not a great indicator of a soil impact, because there's an ability for the plant to compensate and adapt. How do I get that timing? Well, I measured, this is in tomatoes, so I measured canopy temperature. There's canopy temperature relative to a wet reference, and his, we'll be talking about his work on a dry reference. I picked 3 well-watered crops as my wet reference. There's a relationship here, 0.02 of a degree per kilopascal drawdown in matrix potential. But I had in 4 crops. In 2 crops, though, there's a very different relationship. There's a 5 times increase in temperature as you dry that down. Now, why is that? That was because those 2 crops were diseased. So even though you think you're measuring something, plant canopy temperature as an indicator of water stress, if there's something else that can affect that, it's out the window. And unless you're observing that sort of thing, you will draw the wrong conclusion. Now, because I couldn't use canopy temperature, I did the same thing again. I accumulated crop stress days, too wet, too dry, using matrix potential, and you can see I've got a pretty strong relationship there for these tomato crops. There's a foliar disease. Because the disease in that crop was associated with waterlogging, it ends up on that line. But waterlogging, water stress, so they're not doing the irrigations right. No, that's not correct. Cause, condition, effect. You need to drill down. So we've got an effect. We've got lower yields. We've got a condition. We've got waterlogging and water stress. But the cause is the interaction between irrigation system and soil type. I'll be very brief. These are the chromosols. These are the vertisols. This is imagine a vertical slice through the bed. The drip tape is the yellow line. Red and yellows are too dry for tomatoes. Wet, good is blue, and saturated is in the black. And you can see these sites here, there's a really sharp differentiation between where the plant's going to be happy and where it's going to be too dry, and here too wet. So we've got a happy root zone here, here, and we notice in the vertisols our contours are horizontal, and we have a far more uniform distribution of water. The other thing, these are, oh God, look, I'm going to forget this. That's the standard error of the variance of the mean of that number, which is the saturated hydraulic conductivity from a bore permeameter at the depth of the drip tape. And you see, you know, apart from that one, 27, 25% roughly, these are double. The chromosol is far more variable than the vertisols. So we've got a dual porosity sort of thing in the chromosols. We've got non-porous PEDs and we've got dominant crack flow. The vertisols, we've got capillary flow. We have fine pore size, we've got a fully swollen source because these are irrigated every day, and we have capillary flow upwards and laterally from the emitter, whereas we have downward flow of water from the emitter in the chromosols. So there's an interaction between the irrigation system and the soil type. We're talking soil physics. You can support your soil physics if you understand process with some good old soil chemistry measurements. So surface soil electrical conductivity on a 1 to 5. If you are subbing, you're going to have water evaporating off the surface and you're going to leave salts in the surface of your bed, all right? If water is predominantly moving downwards, they're going to take the salts with it. Surface soil EC, it's quite high here, and we estimated leaching fraction is quite low. Leaching fraction being crop water use minus water applied, and that's the drainage water. But we've got, surface soil quite low, and so we've got a lot of water moving down and not much water going up, hence the strength of that relationship. Over-irrigated, there's a bit of a water table, perch water table there. We can also, obviously, there's effective cation exchange capacity as a surrogate for texture and clay mineralogy. And we can see here in the heavier clay, predominantly 2-1, self-mulching clays, quite tight, capillary upflow, subbing, and not much downward movement compared to the lighter textured chromosols up here. How are we going? 1 minute. So, my opinion, I don't think lab measurements are, for me, a good way to go, and not because I don't think that they are necessarily reflective of real world conditions. They're quite labour intensive. They are a point in time. I think if you use in situ measurements, the temporal and spatial resolution you can get, and there will be talks later today which will expand on this, you get a better understanding of causation. Measurements should be fit for purpose. You need to understand the system that you're dealing with and why you're taking those measurements. If you're looking at an effect on plant growth, then I would suggest that matrix potential is the better way to go because it's more directly with how hard that water is to get out of the soil. If you're doing water balance or irrigation, say efficiency studies, then you'll want to know where the pools of water are. Volumetric water content will be your measurement of choice. Add matrix potential and you can determine some fluxes. For plant growth, if you're interested in the wet end and you get water logging, measure redox. Pair your sensors. Cause, condition, effect. You need to have a model in your head, do your reading of actually how that system works. You've got a plant in soil, what's affecting it, think about where you're going with it. Multi-parameter measurements. There's a lot of studies, like that study I put up before, they've measured non-limiting water range and then they've inferred things. One, is what you've measured in the lab applicable to the real world? 2, how does it relate to what you're trying to measure and see causation? That one about the example I gave of soil strength, it didn't affect yield. It was something else because it was in the middle of, it's a winter crop, so evaporative demand is low. You've got good supply of water because irrigators are overriding that effect of soil strength by irrigating their crops on time. So think about Liebig's law. You know, it's the law of the minimum. Which one is affecting the plant? Don't just assume that the thing you're measuring or managing or controlling is what's actually affecting plant growth. Yep. And Mark is going to touch on this as well, least limiting water range. We've got theory and we've got practice. There are published limits, but those limits will vary with crop, they will vary with paddock, they will vary with season, and so in situ measurements, I would suggest, are a better way to go.